GMA, sorry, I'm down with that. All right, delta H and Q are basically the same thing, except units are different. That's the key to this problem. I know I keep saying that. This is delta H of citric acid. So when you burn citric acid, okay, combust it completely. So you have like a little container of water, and then you have a little container with citric acid, and you light that on fire, and it burns and transfers all of the heat to the water inside the container. It's called calorimetry. That's all it is. And obviously there's error associated with that, and energy can be lost to the air and stuff like that, into the actual cup or container. But let's assume all the energy is transferred. So you got 500 grams of water, starts at 30. You got 2 grams of citric acid. So it says your delta H of combustion of citric acid is 42 kilojoules per gram. They want to know the final temperature of the water. So you're using Q equals MC delta T for the water. So you have to take this and make it a number you can plug in for Q. You have the mass of the water, that's M. You have the C of the water, that's specific heat. You have the initial temp. All you need is the final, so you need to solve this. Put this number in for Q, but you can't use that number because Q is what? What's the units on Q? Just joules. So, what do we do? So, let's get rid of the grams. First, we gotta get rid of grams. Then we can convert kilojoules to joules, which is Marcia's favorite. There's 2 grams, right? We have 2 grams of citric acid. So all we do is multiply this number by 2. That's it, and that cancels out your grams, right? So you got 42 kilojoules per gram times 2.0 grams. Grams cancel. 2 times 42, 84 kilojoules. We can't use kilojoules in Q equals MC delta T. Q is in J, in joules. So we need J. So it's 1,000, right? So there's 1,000 joules in 1 kilojoule. So you would, if you want me to show you the steps here, it's 1,000 joules over 1 kilojoule. Kilojoules cancel, so 84,000 joules, right? So now that's Q. 84,000 joules divided by 500 times 4.18 equals, I'm going to put delta T. So the way I would do it, you guys can do it a different way if you want. You could put x minus 30, and that would be your final temp, but I'm just going to solve for delta T and then figure out your final temp for afterwards. That's what I would do. I would just get my delta T, but it's up to you. You can do it the other way if you want. So go ahead. Take a minute, solve for delta T, tell me what the final temperature is. Now I just made these numbers up, so hopefully the number isn't like some weird thing. But
it's not too bad.
Alright.
And I forget 132 is like the same question.
It is?
Yeah, remember you like...
Oh yeah, and I told you to put, oh yeah, your test, I
the
screwed
same
it up. Yeah, yep.
Alright.
So you put the same choice.
Mm-hmm.
Okay. Yep, you're good. Thank you, sir. Alright, so 500 times 4.18, 84,000 divided by that number. What did we get for delta T? This is 40? Exactly? 40.2. Okay. 40, so 40. And so what's the final temp? 70, right, because it absorbed the heat. Okay. So I did this one problem with you here. There's a handful of heat concept type questions, whether you need Q equals MC delta T or not, just the concept of energy being transferred. And there are a couple questions about this. What does that number mean? So again, I put these on the midterm even though we didn't really go over the thermodynamics yet because you have learned about this, we have talked about it, especially when we did the heating curves. We did that quickly, but I guess what I'm saying is I think you're capable, you understand enough, I hope, but let's review. What does that number mean?
Amount of energy to raise it 1 gram by 1 Kelvin.
Right, so if I have 1 gram of water, it takes 4.18 joules to raise it 1 Kelvin. So if this number gets larger, so let's say specific heat is 10 versus 4, does it take longer or does it take less time to heat up that substance? It takes a lot longer, right? So metals usually have numbers less than 1. So metals have very low specific heat, which means it heats up very quickly. But it means it also cools off quickly. Okay? So stuff we've talked about in the past, so just keep that in mind that specific heat plays a role with how fast something heats up, how fast something cools down. Questions with this? Okay, so another question that I will be nice to give you a little heads up on here. Similar question.